Remember that in the last class we had talked about closed strings on the torus, and you remember we have this nice fundamental domain which we had to do the integral over. The fundamental domain was this half strip excluding this unit circle, this region, and the object that we had to integrate had two places where it could go singular. It could go singular here, or it could go singular up there. This part was not in our fundamental domain, so it gave us no trouble. That part was, but then we had a physical interpretation of that as coming from the IR, from long distance exchange of closed strings. Okay? And using that physical interpretation, we checked that the bosonic string did indeed have trouble. Well, firstly, we checked that the bosonic string did indeed have trouble, but that trouble came from the part of the partition function that was 1, corresponding to exchanging the tachyon. When we got rid of that, there was no trouble. The other part, the part that came from exchanging the graviton, was marginal. It was exponentially neither damped nor blowing up, but it was power law dying down. So it meant that there was no trouble. All this you remember, right? Okay. So the main point of today's lecture is now start talking about open strings, but before that I want to quickly run through the same calculations with the superstring. Okay. So let's remember for the bosonic string what we had. For the bosonic string, our partition function was what? For the bosonic string, our partition function was there was this product of 1 over 1 minus q to the power n times, then we had q to the power L naught. L naught was negative, so that's minus 1 by 12. Minus 1 by q to the power. Can somebody remember? Is this 1 by 24? This to the power 26. 1 by 24, 1 by 12, what? 1 by 24, right? Yeah, 1 by 24, right? Okay. So we had this to the power 1 by 24. Then we had this to the power 1 by, then we had q to the power square root q, square root im tau. Yes. Square root of im tau to the power 26. This was the partition function just of the bosons. Then we had the BC ghosts. The BC ghosts gave us what? The BC ghosts gave us one factor of product 1 minus q to the power n, the whole thing square. That was from the ghost oscillators, B and the C ghost oscillators. Then there was this factor, of course, of q to the power 1 by 24 in here, square. This was just going from the cylinder to the from the plane to the cylinder, and then there was that extra factor of there was an extra factor of q, right? How did that go? Just give me a minute. How did that go? This was the ground state energy for the bosons, so that was good. Then there was a ground state. Wasn't there an extra factor of q to the power minus 1 here?
There is a q bar to the power minus 1.
Yeah, q bar. Right. Everything here has a q bar. Yeah, q to the power minus 1 and then times q bar. Yeah. 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 And then we had the integral, which was d2 tau over
This q is inside product or
q,
1 by 24?
q to the power 1, it's square. No. It's you're right. Thank you. This thing came. I'm sorry. Now I got it right. Yeah. This was from the central charge. So let's get that. Sorry. No. There was q to the power minus 1. Forget the q bars. Everything has a q bars. There was q to the power minus 1 because the energy was minus 1. But then we had the 0 point energy. The 0 point energy was plus 26 by 24. Right? Here, this factor was a 0 point energy for each oscillator, which was minus 1 by 24, which is minus c by 24. The BC system had central charge minus 26. So it had plus, so this had q to the power 26 by 24. So this factor was there. There was a square. Then there was this factor. And there was this factor. Okay, so you take the product of these two factors, you get q to the power 2 by 24, which exactly makes this an eta function. Okay, so this factor which came from the ghosts was once again product n is equal to 1 to infinity, 1 minus q to the power n times q to the power 1 by 24. Now the whole thing square. Is this clear? Right? This was 0 point energy. This was the vacuum energy of the BC system on the plane. The lowest energy was because the C operator had dimension minus 1. Okay? And they came together to give q to the power 2 by 24, which made the whole thing an eta function. Okay? This cancelled two factors of that. So we got d2 tau by im tau d2 tau by im tau.
In all the cases, q to the 124 is outside the product. I mean, otherwise it would.
Yeah. Always outside.
Otherwise it would be infinite.
Q to the power 1 by 24. But what I meant is that there's one factor for each of these, but it's inside the square.
Yeah, that's right. Yeah, and also true for the first.
Also true for the first guy. 1 by q to the power 24.
Q to the 1
Product.
over 24.
Q to the 1 over 24. 1 by q. And right, product. Yes. Right. Okay. So now the whole thing was this im tau to the power d. In this case, it was d by 2. So that's 26 by 2. By 2. Okay. But
That is 1 over eta.
right. And the measure over the torus thing came with its own factor of im tau. Can somebody remember what that? Just im tau square, or just, I think we got im tau square. We had one im tau and then an im tau.
I mean, just in the measured problem.
No, I think just in the measure there was just an im tau, and then there was an additional factor. Okay, let's see what happens to this. Let's forget the measure for a moment. Let's just take this quantity.
Yeah.
Okay, this quantity now has eta of 1 over eta of tau to the power 24,
26.
but this im tau to the power 26. So square root im tau to the 24, and then 1 over im tau. Okay, and then the original measure came with d2 tau divided by im tau itself. So the whole thing became d2 tau by im tau square. This was a modular invariant measure. This is a modular invariant object. So the whole thing was modular invariant. Right? So the measure was the measure associated with some sort of density. And then there was an additional factor of im tau from this thing. Okay, so now before proceeding to the open string and the unoriented string, which is what I really want to do this lecture if we get there, I want to do the same calculations for the superstring, just so that you're familiar with how that works. Okay, so the superstring now has 4 components. Okay, there's the x, there's the BC, there's the beta gamma, and there's the psi, the fermion field. So we have to deal with each of them one at a time. Okay? So the measure as before is d2 tau by m tau. This is the measure factor. Now we have to write down an integrand, one for each factor. Okay? And for the x fields, of course, it's basically what we've done. So what we will get is, I'll absorb one factor of m tau from the x fields once again. So now you see what we will get is eta of tau times square root m tau. We will get to the power 8 because the BC part is unchanged, okay, except for an additional factor of q. We'll deal with the q part in just 1 minute. There's some hanging out factor of q which I'll deal with in 1 minute. But apart from that, whatever the x was doing is once again cancelled by what the BC is doing. Now it's not completely cancelled, and then you got this to the 8. Once again you get that additional factor of 1 over m tau square to complete the measure, because the ghosts cancel everything but the zero mode part of the x integral. Okay, but now what about this additional factor of q? You see, here you had q over 26 to the power 24. Okay, here we had q over 26 to the power 24 times q to the power minus 1. That made that whole thing q to the power minus plus 2 by 24. The BCCFT continues to have c equals 26. Okay, the BCCFT continues to have q equals 26. Oh yeah, so fine. So this also just continues to work as before. You just get 26 by 24 times q to the power minus 1. Right. So this is just completely unchanged. Yeah, there is no. No. Right. Yeah, there is no issue because 26 is not changed.
Yeah, I mean it's pulling down just a factor of 2 overall from the
right.
X part.
Right. The 26 is not changed even though we're in we're in 10 dimensions. The BCCFT continues to have c equals 26. So this part just doesn't change. Okay. So this part is the only change for the bosonic string is that this power 8 was power 24 in the bosonic string. Now we have to deal with the fermions. And we have to deal with the beta gamma CFT. Okay. Now the fermions we dealt with in great detail in previous lectures, right, last semester. You remember there were these boxes. We talked about how you made modular invariant partition functions for the fermions. Type 2a had one modular invariant partition function. Type 2b had one modular invariant partition function. One thing that we didn't carefully do in that discussion that I wanted to complete here is to understand how it happened. If you remember that discussion we did in light cone gauge. We acted like there were only 8 fermions. Okay?
Now with the DRST.
Yeah. Now, since we're doing everything so carefully here, we're talking about how we've got the X CFT, how it's cancelled by the BC hosts. We're doing the path integral really honestly. We don't want to suddenly jump to light cone gauge. So I'd like to complete that discussion by showing you that if you work in the covariant gauge, that the beta gamma system CFT, that path integral, basically cancels one of the X oscillators to give you the same answer that you would have got in light cone gauge. Okay? So this is the discussion that I want to very quickly have with you so that we completed that part of the story. Okay. How does that part of the story go? Well, it goes somewhat like this. Let's remember what the discussion we had with the fermions. If you remember what we did, okay, if you remember for the fermions, we had various possible boundary conditions. Okay, so there were 4 boxes that we kept drawing. Okay, and these boxes were minus, minus. That was the trace in the Neveu-Schwarz sector. Neveu-Schwarz sector was antiperiodic on space, and because it's an ordinary trace, it's antiperiodic in time. Okay? When we got minus plus, because we were imposing minus 1 to the f. Though, you know, what we did when we worked it, I'm just going to remind you what we talked about last time, and then I will connect it to how you get it from the BCCFT system. Okay? So, what we did was we reminded ourselves that, okay, I'll put the signs in a minute. That's the complicated part, but let's first do this. Then there was the Ramon sector with the minus sign, ordinary trace in the Ramon sector, and then there was the sector with the plus sign in the Ramon sector. Okay, now if you remember, we had a minus here and a minus here. And then this was either plus or minus depending on whether we were type 2A or type, the relative plus minus was whether we were type 2A or type 2B. Okay? And the whole thing was by half. Okay? Then we gave a Hilbert space interpretation of this object. The Hilbert space interpretation of this object was that, and then this whole thing then went to the power 8. Because we have 8 fermions, all of which were together in the Ramon sector, or all of which were together in the Neveu-Schwarz sector, right? So it was this to the power 8 of 4. Sometimes we coupled 2 of them together and called it 4. I'm going to call it 4. If you remember the way we did the calculation, we combined psi and psi bar together, and each of those was counted as one factor. We had these Z alpha betas, which were combined psi and psi bar, and we had those to the power 4. So we had this to the power 4, minus this to the power 4, minus this to the power 4, minus this to the power 4. And I just want to remind you where the various signs came from. Okay. Where did this sign come from? From the Hilbert space point of view, this was half of 1 plus trace of minus 1 to the power f. But it came from the fact, if you remember, that we argued that this plus became minus because the host vacuum carried minus 1 to the power f is equal to minus 1. So the identity operator carried minus 1 to the power f is equal to 1. But the host vacuum, you remember, was the vertex operator for that had a factor of this e to the power phi. And any integer shift of phi changed the fermion number by 1. Okay, the gamma, the vertex operator corresponding to the operator gamma was e to the power phi times e, that eta thing, field. You remember that, right? At least vaguely. Okay, so this was our argument then. This was a plus, and there was a minus. Even though we were asking for the whole theory to have minus 1 to the power left equals plus 1. So we wanted to put this sign. We rationalized this sign by saying that when we dealt with the ghosts, it would become a minus. Right? That the cancellation between the ghosts and the oscillators would be up to a minus sign for this sector. This is the kind of thing we want to see now. Okay? Then this sign was just minus, and that we were sort of happy about. We were happy about because this was spin statistics in space-time. Okay? This was the sign that told us that anything that came from the Ramon sector, therefore something that could contribute to a partition, a space-time loop with fermions, would come with a minus sign. And this was the relative sign about whether we were imposing trace minus 1 to the power f is plus 1 or minus 1. Remember in the Ramon sector we imposed one or both of them. If they were the same, we were in type 2b theory. If they were different, we were in type 2a theory. All this you at least vaguely remember, right? Okay, So this was the partition function that we said we were going to multiply this with. And this is going to be our final answer. This is what's going to appear on the right hand side for the superstring. This times that. And for these we had very particular concrete expressions which you can look up in Polinsky, or you could go back and look up your notes. Okay? The thing that I want to do very quickly, well, there are two things I want to do very quickly. The first one is to show you that this honestly follows, okay, from the beta gamma system. Okay? So let us remember what each of these objects was. I'm going to just quote the formula we had from Polinsky, and then we'll try to see if this formula, if we can honestly see that we can cancel one of the factors using the beta gamma systems. So where was the formula for the fermions? Modular invariance. Yeah. What Polinsky defined was Z alpha beta for a pair of fermions. So Z alpha beta tau, which was trace in the alpha sector of e to the power minus of course q to the power h times e to the power I pi beta q, where q was equal to 1 for psi and q was equal to minus 1 for psi bar. So q is fermion number. Okay? And I'll remind you what for Polinsky what alpha was. Alpha was psi of sigma plus 2 pi is equal to psi of sigma times e to the power pi, I into pi, I pi into 1 minus alpha. So extremely convoluted definition. Remember that alpha equals 1 from this definition is no phase and therefore Ramond. And alpha equals 0 from this definition is a phase and therefore NS. Okay? And putting beta equals 1 is putting a factor of minus 1 to the power f. Putting beta equals 0 is not putting a factor of minus 1 to the power f. Okay? So this formula in equations became half z 0 0 because it is Neveu-Schwarz with no minus 1 to the power f minus z 0 1. Okay? This to the power 4 minus z 1 0 to the power 4, and then minus plus or plus, yeah, let's call it minus plus z 1 1 to the power 4. Right, z 0 0 minus z 0. I'm sorry, and Polinsky writes z. Oh, z alpha beta. I wrote it, but I got this wrong. So this would be z 0 1. This would be z 1 0. This would be z 1 1. Yes, it is correct. Right, because this is alpha, both Neveu-Schwarz. This is alpha, both Ramond. No minus 1 to the power f, minus 1 to the power f. No minus 1 to the power f, minus 1 to the power f. Right? So now if we honestly did the calculation, what would we get? If we honestly did the calculation, what we would get, let's say in the Neveu-Schwarz sector, would be z 0 0 to the power 5 plus z 0 1 to the power 5. This is what we get for the fermions. Right? That's what minus 1 to the power f would give us. Right? So now what we want to do is to honestly do the same calculation also in the BCs, in the beta gamma system. In each sector. Remember that the sectors for the beta gamma system were the same as the sectors for the fermions. That is, if you put the fermions in the Neveu-Schwarz sector, you had to put the beta gamma system in the Neveu-Schwarz sector. And similarly for the similarly with the -1 to the power f's. Okay? And you remember that we discussed that that was necessary for the BRST charge to be conserved, because there was a term in the BRST charge that was fermion times beta, fermion times gamma. For that to be single valued, we needed that the beta and gamma and the fermions had the same boundary conditions. Okay? So very good. So if we are in the Neveu-Schwarz sector with no -1 to the power f for the fermions, we're also in the Neveu-Schwarz sector. So that is the beta gamma system is periodic, as anti-periodic. Okay? And we're also not putting a factor of -1 to the power f. Now what was -1 to the power f for the beta gamma system? Well, you remember we had a nice definition. A fermion number was the net sum of charge of the bosonized fields. Do you remember that our Q, suppose we had some object, a vertex operator which was alpha I hi plus zeta phi, where this was the bosonized beta gamma ghost. Okay? Then this object was associated net fermion number sum over alpha I plus zeta. And there was always some ambiguity in this fermion number, but there was no ambiguity in -1 to the power f. And we only ever use -1 to the power f. Okay, we're going to compute this, but with beta equal to either 0 or 1. So where it's non-trivial, this is -1 to the power f, so it will be completely unambiguous. Okay? And let me also remind you one last couple of things. In the NS sector, the vertex operator corresponding to the vacuum, the lowest energy state, was e to the power -phi times eta or something like that. One of the two, eta, zeta. I'd have to look it up. This will play no role. The point was that was e to the power -5. And this had h is equal to half, I believe. Whereas there was e to the power -5/2 in the Raman sector. And this had h is equal to, I believe, 5/8, 3/8. Let me check that. Maybe it's 3/8. 3/8. Okay, now with all these reminders in place, we can very quickly go and do the calculation. Okay, I know it's some time since you saw the beta gamma superghost system, but at least you vaguely remember this, right? You can go back to your notes and look it up. Fine. Okay, so now what we want to do is to compute. I'm going to do the calculation in the NS sector and leave it as an exercise for you to do the same thing in the Raman sector. Okay. Now what we want to do is to compute this object and this object in the NS sector for the beta gamma system. Okay. So, well, in the NS sector, both beta and gamma are half integrally modal. Right? Okay. In the NS sector, so what we want to do is to compute trace of q to the power L0 for the beta gamma system. So let's first do the oscillator part, then we'll look at the zero point energy. The oscillator part is what? The oscillator part was product of n is equal to z plus half, product over half integers, 1 plus q to the power n So let me be more specific. N is equal to half, 3 halves, 5 halves, positive half integers. Clearly, and then square. This is one set of oscillators for 1 over. 1 over this. Why 1 over? And with a minus. Why 1 over?
Bosons.
Because they're bosons. Okay, excellent. So we get this factor of 1 over 1 minus q to the power n. Whereas here, no. I believe we're going to get 1 plus. Why? Just a minute. Sorry. We're going to get 1 plus. So I'm sorry about that. Why is that?
Because of the molding.
Because of
the
anti-periodicity. Exactly right. You see, what we're doing is computing a determinant. The determinant is that over anti-commuting fields. Okay, so because they're bosonic, you get it in the denominator. But because they're anti-commuting, it's going to be exactly the same kind of determinant you would have got for fermions. Because as Upmanyu said, if you actually worked out the moding in the time direction, because they were anti-periodic, they would be half integrally moded in the time direction. And that half integral moding in the time direction would give you this effective plus. Okay? So this looks odd, because normally we think of bosons with coming with a minus, but this is an odd theory. It's bosons, but the fields are anti-commuting. Canonical quantization isn't giving us the right answer. Right? Okay, it's a strange theory. Okay? And if you work out the determinant, you'll just get this. It's because the moding is wrong, as you said. Okay, excellent. So far so good. This thing's square, but now we need also we also need the additional factors. So this is for the first term. This is for z00. Okay, so there's this. Now what about the ground state energy? First we get a factor of q to the power half, because this was the ground state energy in the ns sector. This is the analog of the q to the power -1 for the BCCFT. Then we get the factor from the central charge. Now, the beta gamma system had central charge equals 11, right? Because -26 plus 11 is -15, which is the central charge of the 10 x's and 10 size. Okay, so beta gamma system had a central charge equals -11. So we're going to get this additional factor of q to the power plus 11 by 24. Okay, and let's add this up. So that is so it was q to the power. That's q to the power 23 by 24. So that's okay, fine. So this is q to the power 23 divided by 24. And let's look at what we get from the psi part. From the psi part, Polinsky reports q to the power minus 3 alpha squared minus 1 by 24. And alpha in this case was 0, right? Yeah, alpha was 0, so it's minus 1 by 24. Now, how are the q powers working out? Just 1 minute. Have I got these relative signs wrong? Just a minute. Yeah, had this been 12 by 24 and minus 11 by 24, then we would have more or less done. Wait, have I got the signs wrong? Just we wanted q to the power L0. L0 was plus half, right? Let me check that. Sorry, people. It was minus half into, so we have e to the, I'm sorry, this was minus half, right? Of course, yeah. Why? Because, you know, remember that we had the beta gamma system. This was just the weight of the gamma operator. The vacuum was just the weight of the gamma operator. Vacuum was created by the gamma operator. Remember, this had weight 3/2 and this was weight half, minus half. Like this, just 2 and minus 1. All good. Sorry for that mess up. So this is q to the minus half. So now we get this whole thing here is q to the power minus 1 by 24. Okay. So we get q to the power minus 1 by 24 divided by q to the, okay. So the net contribution of the ghost is this. It's 1 over 1 plus q to the power n, the whole thing squared, product over n, and then q to the power minus 1 by 24. And is that what we need to cancel the fermion part or not? Should be, because that was q to the power, just one. I'm sorry, just give me one. I'm getting the wrong sign. It's almost right, but the wrong sign. because this is coming in the numerator. The fermion thing also came in the numerator with the same q to the power minus 1 by 24. I wanted to cancel one factor. Somehow I'm messing up on this. So it's q to the power minus 12 by 24 plus 11 by 24, right? Give me one moment, please. Where am I missing? Just give me one moment, please. I'm sorry. I just do this calculation. I keep getting the song every time I do this signs I get differently. Firstly, what is this power? Firstly, from the central charge. This is an object with positive central charge because it had plus 11. So this should be minus 11 by 24 because L naught is minus 11 by 24. So last time I wrote that, I got that even wrong. Okay. Then q to the power, this is either plus or minus half. Let me just get that straight. But it's either plus or minus 12 by 24. If it was plus, this would match perfectly. It is half. But now I've confused myself because I thought that the vacuum corresponding to was the state corresponding to the eta operator. No, in fact I was wrong. The vacuum was the state corresponding to the operator e to the power minus phi, not zeta times e to the power minus phi. And this object did have h equals half, but that zeta had thing had h equals minus 1. Fine. So, sorry, I just my repeated confusions. Let me say it again. The vacuum state does have h equals half, and that is consistent because if you remember when we did the state operator map, we found that the operator corresponding to the vacuum in the Navier-Stokes sector was e to the power minus phi. Now this gamma operator was some eta times e to the power minus phi, where eta had dimension 1, minus 1. That's how it shifted the half to minus half. Okay, but the operator dual to the ns vector was not gamma, but e to the power minus phi. Okay, so h was half. Okay, so now we're totally fine. So this is this thing here was q to the power 12 by 24. This was q to the power minus 11 by 24. Add them up, you get q to the power plus 1 by 24. Okay, so that cancels the 0 point part of the fermionic Z00, which came with a q to the power minus 1 by 24. And the oscillator part obviously cancels, because the oscillator part of the fermions was exactly the same thing, but in the numerator. Okay? Great. So much for Z00. Now let's look at this guy, Z0, 1. Okay. Here the question is, what is the Q charge of the ghost vacuum? But because the ghost vacuum is precisely e to the power 5, by a definition of Q charge, the Q charge of the ghost vacuum was -1. Right? Because the Q charge is the sum of all these coefficients. There's exactly one coefficient here with 1. 1 minus 1 doesn't matter. Okay? So e to the power minus I pi q was -1. This is why in this sector, the BC CFT contributes with a minus sign. Sorry, beta gamma. The beta gamma CFT contributes with a minus sign. Now, the rest of the oscillator business is exactly the same. That is what we're going to get. So let's write it down. Where am I writing? What we're going to get is this with a minus sign. Because every time we have a new beta gamma oscillator, it flips -1 to the power f by -1. Because the beta gamma oscillators themselves carry -1 to the power f, charge 1, q charge 1. Your -1 to the power f is 1. Okay? So, but the oscillator part just picks up a minus sign. But precisely the same thing had happened with the fermions. The fermions with -1 to the power f had a factor of 1 minus q to the power n in the numerator. For exactly the same reason. Because the state with a fermion and a state without a fermion differed by a factor of -1 to the power f. I mean, -1 to the power f was -1 in one state if it was 1 in the other state. Exactly the same reason. So the oscillator parts continue to cancel, but there was this overall minus sign. And that is the origin of the overall minus sign here. Okay? So the honest calculation would be to get this with a 5 and then cancel one of the powers here. To get this also with a 5 but cancel one of the powers up to a minus sign. So the minus sign didn't come from the fermions, but it came from the beta gamma ghost. Do you understand? I'm sorry I've been so haphazard in this discussion. I'm sorry this, I hope this Q part, which was basically inessential, I mean basically not, I hope this didn't confuse you. Was this clear? Was the Q cancellation clear? Okay, excellent. Now I'm going to leave working out the Ramon sector. I'm going to leave working out the Ramon sector to you. Basically, you would have to do this. Yeah, I'll just leave it to you. Basically, what's going to happen is, you remember that in the Ramon sector, the fermions themselves. In the Ramon sector, the fermions themselves carry a certain weight, and that is encapsulated in the 0-point energy in the Ramon sector. Like the zero state of the Ramon sector has a weight coming from the fact that it is e to the power alpha I hi. Each of these alphas is plus minus half. Okay, so you get a weight which is sort of like 5 by 8, if I remember right. Okay, that is captured in Polinsky's formula for the fermions. But the beta gamma system also has a certain weight, namely the ground state energy in the Ramon sector. Okay, the ground state energy in the Ramon sector was this 3 by 8. Okay, it's different from half. That difference will plane and cancel the additional factor that you need in the Ramon sector. Is this clear? Would someone like me to work this out? Or? Okay, it's a similar kind of logic. We'll take 10 minutes to get it straight like we did last time, then we'll get it straight. It will also cancel 0-point energies. In the Ramon sector, once again, you get these powers of 4. So this is a triviality, I mean more or less a triviality. It's more or less guaranteed to work. But I just thought I would, we discuss it once, particularly since Polinsky very irritatingly doesn't work it out. Says it cancels, okay. Fine. Okay. So, but it's nice just to see it work. Okay? Clear. Very good. So the last thing I wanted to say about the closed string was that now what we have to do is this d2 tau by im tau, the whole thing square, times this object, right? 1 by square root im tau times eta of tau, the whole to the power 8, and everything will be mod square. Right. So, right, I really should, okay, because the im tau comes with eta bar to the power 8, and then we get one factor of this and its complex conjugate. So half z plus z plus z plus z mod square. Schematically, well, that factor is this object here. That's the quantity we really have for the torus partition function. Now, actually this quantity is 0. When you do work it out, it's 0. And physically, why does that happen? Space-time supersymmetry. This quantity computes the change in the vacuum energy, and that's 0. But were you to put vertex operators, we're looking at the simplest torus amplitude. Were you to add vertex operators, now it will no longer be 0. So all the structural features that we're talking about, you might think are totally trivial because we're talking about structural features of something that's 0. But every structural feature I talk about will survive when you also have vertex operators. So we'll ignore the fact that it's 0 and analyze this. Okay? And now, once again, if you try to analyze the finiteness of this quantity, of course it's finite because it's 0, but then the vertex, once you add vertex operators, it's no longer 0, but it will continue to be finite. When you do this integral over this upper half plane, okay, when you do the integral over the upper half plane, then what we're doing here is looking at tau is equal to like IT, where t is very large. Okay, so then this quantity here, apart from these im taus, is effectively, as you see, the oscillator partition function in light cone gauge. The oscillator partition function in light cone gauge after GSO projection. So what we're doing is calculating trace q, but q was e to the power I tau, and tau is equal to IT. So minus t times L0 for L0 very large. Okay? So this is receiving its maximum contribution. This is receiving its maximum contribution from the state with minimum L0. And the whole point here is from the oscillator state with minimum L0. But remember, L0 was proportional to mass square. This L0 includes all 0-point contributions. So including everything, L0 is proportional to mass square. So this receives its maximum contribution. The GSO projection is incorporated here, all these minus signs and so on. So the vacuum state does not contribute. The vacuum state would have had a negative L0 because of all the 0-point stuff. But that does not contribute, which is same as the statement that the tachyon is projected out by the GSO projection. So the first state that's contributed is the first state that survives the GSO projection, which is the graviton. That had L0 equals 0. So the leading divergence here would be L0 equals 0, just constant. And then the fact that we had this im tau to the power 8 makes this a convergent integral. Okay, so we had this, it's effectively like dt over t to the 5, because there was 8 and then there was an extra 2, or maybe even t to the
4
6.
plus 2.
6, yeah. So it's nice and convergent, no problems. Okay? So the scattering amplitude in the superstring is just completely convergent. And you see the point is this, that there is only one end of moduli space, of the integral over moduli space. But by viewing it, it's your choice whether to view that end as UV or IR. We've chosen the domain, fundamental domain, so that we view it as IR, but of course that's just some trickery. But the point is that once we make that choice, it is manifest that there is no divergence. Simply because the only thing, you see from the structure, the only thing that could have led to a divergence was a particle of negative L0. A particle of negative L0 translates into space-time into a tachyon. And the very fact that there is no tachyon, therefore guarantees that there will be no divergence. This general structure doesn't care about what kind of oscillators you have here. If there's no negative energy state running in this trace, you can never have this divergence. Is this clear? So this is how string theory makes gravitational amplitudes finite. Now I've gone through this in so much detail because this is in the end a very non-trivial accomplishment of string theory. We tend to forget it because we don't use it so much in our day-to-day lives anymore, but it's an extremely non-trivial thing. I want to emphasize why it's so non-trivial. You know, you might take the point of view, you might say, well, you know, in modern quantum field theory, divergences aren't really a problem. We use Wilsonian renormalization groups. So why are we so obsessed by getting things finite? But you know, in strings, it's actually very hard to take a theory of gravity and to regulate it in a way that preserves diffeomorphism and invariance, and therefore does not introduce ghosts. And you know, you see this in string theory, we'll see this as we go along, but you see this in string theory repeatedly. The structure of string theory is extremely tight. Okay, the way string theory sort of regulates the path integral is somehow very carefully chosen. If we were to try to add one more particle into string theory, that would destroy everything. We can't take string theory and then have it interact with some quantum field theory. That just destroys the consistency of the theory. It's very balanced and poised on edge. You know, so string theory somehow, we're doing this Schwinger-Keldysh, the Schwinger, you remember how we had in the last class, we went to going from the integral over this tau to the integral over Schwinger parameters. Now, how would you normally regulate an integral over Schwinger parameters? So you have some e to the power minus t, you have some e to the power minus t, and then maybe what you would do is to add some term to this integral. You don't want let's say small t to contribute. Small t will correspond to high energies. So maybe you could put times e to the power minus a by t, some regulator by hand. That's the kind of thing we do in quantum field theory. You add some regulator. If you try to add some regulator like this, you would destroy the modular invariance of the theory. Okay? Or maybe something else you could do is just cut off the integral. Say, don't integrate t all the way down to 0. Stop it at some point. That would amount to here, schematically, taking this moduli space of string theory and introducing a boundary on it. But I don't know if you remember, when we argued that BRST states decoupled, the way it went was this, that if you took a vertex operator and you performed a BRST transformation and you didn't get 0. Exactly. You got an integral over moduli space. And then when you did that integration over moduli space, that went to 0, assuming that moduli space had no boundaries. Do you remember this? If you suddenly take moduli space and introduce a boundary in it, that argument that the BRST states will decouple will no longer be true, and you will have violated unitarity. This is typically what happens in attempts to regulate gravity in some stupid way. You know, you take some latticization of gravity, or you do something that violets. You try to regulate gravity by Pauli-Vilas regularization. You always introduce unphysical ghosts, unphysical poles into your propagator. You violate unitarity. Okay? And you can see all of these remnants of all of this in string theory. You try to do something sort of silly to regulate the string theory path integral, you'll violate unitarity. But the great thing about string theory is you didn't have to do anything. It was automatically regulated. So many things came together to make this happen. It's somehow very beautiful. It's very important that this moduli space actually, though it looks like a strip, there are no boundaries in this moduli space. This part is, so this edge is identified with this edge because tau goes to tau plus 1 is the same. And this part also folds on itself. This thing and this thing meet up. You should try this. Investigate this moduli space carefully. You see, this moduli space is actually a compact moduli space. So the integral over moduli space is an integral over a compact space that was very necessary to the consistency of string theory. Okay? So this whole thing is working very beautifully in a way that's very tight. You can't somehow mess it around. You can't change the regulator. At least we don't know how to do that in a way that preserves consistency. And something to remember. The one consistent theory of quantum gravity we have is very tight. It doesn't allow you to fiddle around. Okay, fine. Let's move on. Any questions or comments? I now want to move on to the open string. Questions or comments? Wonderful. Now let us suppose we're in a situation where we have not just closed strings but also open strings. Okay, so our open strings are a strip. They run from 0 to pi. Okay, the open strings are a strip. They run from 0 to pi, and we want to do the analog of the torus path integral, which in this case is just going to be a cylinder path integral. Right? Because what we've got is some open string, and it's got a boundary here, it's got a boundary here, and it's going to go around in a loop. So you see that the topology is that of a cylinder. Okay, great. So first we're going to work out the integral, then we're going to try to interpret it. Okay, excellent. So let's first work out the integral. Let's start as usual with the x CFT. Then we look at the BC, then we look at the psi, then the beta gamma, and so on. Okay, so for the x CFT, what do we have? So what we want to do is to work out trace, let's say e to the power minus, let's use Polinsky's notation. Whether he uses q or not. Trace e to the power minus 2 pi TL0. Okay. Actually, the first thing to remember here is the following: that the moduli of the modulus of the cylinder has just one real number rather than two. This is because the cylinder is defined by saying that we have a boundary at 0 and pi. So something that tries to tilt this will change the location of the boundary. So that's not allowed. In our problem, 0 and pi are special points. Okay? So clearly what we can do is change the aspect ratio of this and this. But we have to keep them orthogonal, because the ends of space have to lie at 0 and pi. So there's clearly only one modulus, namely the ratio of this guy to this guy. For the torus, that was a modulus, but we could also tilt. But the tilt is gone because we've got fixed boundaries. Is this clear? Okay. And if you work out the measure coming from the measure over moduli, like we worked it out for the torus, you'll find the analog of d2 tau by im tau is dt by t. Okay, so this is what comes out just from the measure, the open string measure over the cylinder. Then we have to compute trace e to the power minus TL naught. And we have to compute it over all the CFTs. Okay, so let's first remind ourselves how it goes for the X CFT. For the X CFT, as far as the oscillators are concerned, maybe you remember that the spectrum is exactly the same as one side of the closed string. Okay, so the oscillator part is very simple. It's dt by t. Then product over 1 to infinity 1 minus e to the power minus 2 pi tn. I've deliberately not put this q here. This is like q, but q makes you think of a complex number. Just to make it clear that this is actually just a real number, I'm writing that as e to the power minus 2 pi t. Okay. Now, this is the oscillator part. Okay. What about the 0 point energy? Same thing. 0 point energy is exactly what it would have been for one copy of the closed string, simply because there are only these many oscillators. 0 point energy comes from Casimir energy. The number of oscillators is just one. So for each oscillator you get what you got. So this comes with its power of q to the power, now that was minus or plus, t by 24. Q. Outside, thank you. E to the power minus 2 pi t by 24. Okay, and then this is to the power d. Let's say we know that we're working now directly with the superstring. So we know that it's 10. Is this clear? Now, what about the powers of t from the 0 modes? Well, if you keep track of the factors of 2, there's a small difference between the open string and the closed string, because this length was pi and that length was 2 pi. So you work out the effective mass for the 0 mode for the open string, it's a bit different. But we were never doing the calculation with that degree of precision. We were just keeping powers of t. So as far as powers of t go, this is just t to the power 5. I make a t squared times square root t to the power 8. Is this good? Was this too fast? Sorry. Thank you. Thank you. I'm keeping 8 because I know that something's going to cancel this, right? Okay, great. Now, what does the BCCFT do? The BCCFT, exactly, the calculation is exactly the same as before, because BCCFT also behaves like one copy of holomorphic. So exactly as the same as before, cancels this, the same central charge business and so on. So this just becomes 8. Okay, that's very nice because the square root t to the power 8 times this if we want, is t to the power 8 by 2 times eta of it to the power 8. So this is nice, and it has some sort of modular properties that we will talk about in a bit. Okay? All good? Excellent. Excellent. And then we've got dt divided by t squared times 1 over this business. Okay? And then if we're working with the superstring, okay, if we're working with the superstring, once again we get the same factors of these z, 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 z. Once again, the cancellation works exactly as before. So this to the 4, this to the 4, this to the 4, this to the 4. We just need one copy of the holomorphic part. Let's say we're working with a string where, yeah, you remember the boundary conditions for the psi fields, right? It was just psi plus minus is equal, right? It's the ordinary open string boundary conditions for the psi fields, similar boundary conditions for the beta gamma system. All of it is encapsulated in saying that it's effectively one copy of the holomorphic part. And so instead of having this mod square, we just have this, and we're happy. Okay, so at the level of calculation, this is what we get. Looks very similar to the closed string. However, at the level of physics, this is very different for a reason we're now going to explain. Okay. So, the really important thing here is the following. The domain of integration of t runs from 0 to infinity. This is because there is no, had we had a rectangular torus, there would clearly be overcounting to integrate from 0 to infinity, because all that's physical about the torus is the ratio of the two sides. Which side is smaller and which side is bigger doesn't matter. So t and 1 by t are the same torus. But here for the cylinder, there's no symmetry. One side has ends, the other side doesn't have ends. So this cylinder is very different from this cylinder. Okay, you have to integrate over all inequivalent Riemann surfaces. So clearly the integration is going to go from 0 to infinity. Is this clear? Okay. Now we are in a slightly tricky situation. Now we're in a slightly tricky situation for the following reason. You see, in the case of the closed string, we said, well, there was only one end of moduli space which we could interpret as the IR. Okay, and there is one end of our moduli space here which we can interpret as the IR, namely t goes to some very large value, because that describes an open string propagating over very long distances. Because t is like the Schwinger parameter, t multiplies p square. So if t is very long, q is very small, that's the IR. Right? So this is the IR of, this is the UV, and they're not the same. So here you might genuinely have a UV divergence. It might seem as if IR physics will not control the UV, and then we might be in trouble. How does that work? Okay, so first, before looking at the UV, let's actually just look at the IR. So the IR is once again large T, and the discussion is exactly the same for closed strings. This quantity could possibly give rise to trouble in the IR only if there was a tachyon in the open string sector. But the GSO projection, because this open string sector is 1/2 of the closed string, the GSO projection makes sure that there is no such tachyon.
But projection, I mean, it's also possible to.
Yes, we're going to do the same projection that let's say we're going
The
to
same projection
as we did for type 2 for type 2 theory. At the moment we're going to do this. We will later try to explore whether there's anything else we can do. Okay? But you know, in the end there isn't going to be, for the reason that we're going to talk about in a moment. The point is that open string theories can also be viewed as closed string theories.
Open closed duality.
Because the same Riemann surface, we'll see this in a minute, but the same Riemann surface, which can be thought of as one loop for open strings, can be thought of as tree-level propagation for closed strings.
Right.
And it had better be that in the closed string sector, we're imposing the GSO projection. Okay? So that will constrain what we can do on the open string sector. Okay? So at the moment, let's assume we're doing the same thing. We'll come back later to see whether there was anything further else we could have done. Yeah, but at the moment, we're just imposing the same GSO projection. Okay, but good question. Fine, but let's assume that we've imposed the same GSO projection. Then it's just the same story. The large T behavior is fine simply because there is no open string tachyon. Is this clear? This makes a lot of sense physically. In the IR, you should have had problems only if there was some IR problem in your theory. A typical IR problem is an instability. If the theory has an instability, you have an IR problem. Theory has no instability, no IR problem. Physically very sensible. Is this clear? What about, however, the UV?
Blows up badly.
Yeah, looks like it blows up badly, but let's check it. Okay? Now, let's check it in the following way. What we're going to do is to use modular invariance. This quantity, whatever it is, just 1 second. Check one power. Ah, yes. You see, this quantity, whatever it is almost modular invariant. Why is it not completely modular invariant? Let us remember, firstly, this quantity, there was no reason for it to be modular invariant because the cylinder was not, had no. However, the formula looks like it's very close to being modular invariant. Let me remind you what I mean by that. Okay, this part by itself, this is just the torus partition function at a square value for the modulus of the torus. So this part, the part that comes from the fermions, just has a modular property. So it has z of 1 by t is simply equal to z of t. Right? Yeah, not even a minus sign. Because suppose this was simply what the torus partition function was at tau is equal to it. But we know that z of tau was modular invariant. So z of tau is equal to z of minus 1 by tau. But minus 1 by tau is just taking t to 1 by t. The minus sign comes from the I. So this part, even though it was not needed from physics, just happens to be modular invariant. Is this clear? This part almost happens to be modular invariant. Why the almost? Anyone? Same thing? There's one difference. What is it? Exactly. The part that would have been modular invariant is eta tau bar tau bar im tau to the 1 by 24. This is modular invariant. This we know. But what we have here is one factor of eta, but one factor of im tau. Here, suppose now we set tau is equal to, we take the mod square. This would have come with two factors of eta with one im tau. Okay? So the correct result is this. The correct result for modular transformations is what? It's that eta of I tau mod square. The mod square is just square because, as you can see, it's a real function. Right? So eta, but I'm writing mod square just to make it look nice. Eta of I tau mod square times square root t. That's same as im tau. It. Eta of it times square root t squared is equal to 1 by square root t is equal to, so just take t to 1 by t. So square root of 1 by t times eta of I by t mod square. This is the correct equation. Okay. Now what do we have here? What we have here is the following. What we have here is t, we have a factor of square root t times eta of t of it, and then 8 powers of that. Okay, so I'm going to use that. So just by taking the square root of this and taking the tau t here, can you see that this is the same as eta of I by t? Okay, so this can be replaced by,
since it is real, that's why.
because it's real, because mod square is just square.
Yes.
Okay, so the eta of, so square root t to the eta of it is just eta of I by t.
Without the root, 1 by root.
Without the?
1 by root.
Without the 1 by root, exactly. Because this factor went up there to make it true. Okay, so what is this saying? This is saying that if we take that, suppose I want to know what happens to this whole partition function, not at t large, but at t small. I can compute the whole partition function at t large, because t small is 1 by t large, but there is no factor of, but these t's go away. So I just drop this and replace each of these t's by 1 by t, and that gives me an accurate equation for the partition function. So now let s 1 by t equals s.
Now do a transformation of variable.
Now I'm doing a variable transformation. Now 1 by t equals s, but ds is then simply dt by t square. So do you see that what we have shown is that the open string partition function can equivalently be written as ds 1 by eta of is times to the power 8, and then this z business, which was itself of is to the 4 to the 4 to the 4 to the 4.
Previously, there are two variables for the integration, d2 tau.
d2 tau.
Now it became
Just one variable. Right. But that is not really very important, because when we're talking about very large t or very small t, that's not the really important. But it's true. It's true. Here it's just a real variable. It's a very simple change of variables. Okay? Is this clear? Okay? And now we see something strange happening. Well, we were interested in what happened at very small t. So that is the same thing as what happens at very large s. So now we can say, well, we can just do the same transformation as before. Now we've got something in the IR controlling physics, so it's very light particles that are controlling physics. Great. Very light particles are controlling physics, that's nice. So we just go to very large S. There's no exponential problem. But this whole quantity starts off as 1 plus, actually, 24 plus, because the 24 graviton states, 24 massless states. Not 24, it's 8. 8 plus something times e to the power minus s plus something times e to the power minus 2s, and so on. Right, because the oscillator states in the open string, the minimum one not projected out by GS for projection starts at dimension 0, which corresponds to the photons. Okay, then there are the massive string states and so on. So it looks good, there's no exponential problem. But there's a problem. Exactly. Because this guy here is a constant. We have the same thing when we were looking at the torus. But that constant was ameliorated by what? Why was that not a problem in the torus? Because of the taus. There was tau to the power 6. Okay? So though we were doing integral d dt, this was over 1 over t to the power 6. So there's a power law suppression and it was fine. Is this clear? Now this modular transformation has eaten up that power law suppression, and the part that was not eaten up by the modular transformation was eaten up by a change of variables. So there was no power law suppression. So constant is a problem and gives us infinity. Is this clear? So even though we have managed to transform the problem mathematically into the IR,
we are looking at large S.
we are looking at large S because we wanted to look at small t.
Okay.
But S was 1 by t. So even though we mathematically managed to transform the problem into the IR, it didn't help us because there was no real modular invariance. There was a small violation, and that was the problem. Now, what does that mean? Why is this happening? Is the question clear?
This
Okay.
is not all we have.
Yes, but first let's understand what the problem is. So, you know, what we're doing is this. We've got the string world sheet, and we've got the problem is happening where we're deep into the string, the UV region of the open string, which means the open string is going over a very short loop.
Yeah.
If we blow that up, to make the size of this loop finite, means the open string is very long.
Yeah.
Because these two are conformally equivalent to one.
Yeah.
Now, if the open string is very long, there's another way of looking at this problem that seems more reasonable. That is, cut it like this.
A closed string propagating.
Exactly. So think of this problem as the open string boundary condition being some sort of source that creates closed strings. Then the closed string goes shh, and then is absorbed by another source that creates closed strings. Not unreasonable, because you know, if you've got an open string state, basically what you have is something that can carry energy. And in fact, as we go along in our classes, we will compute the energies, the energy density of d-branes, or the energy density of just the fact that you have open strings, basically by doing this, by cutting this diagram and by computing the energy of the source that's creating this diagram. Okay? But first, let's get some words to this.
I didn't understand this.
Right. Suppose you imagine this, that by putting open strings all over space, what you've done is somehow increase the energy of space-time. Then the fact that you've got these open strings here, okay, would couple to gravity, because gravity couples to anything with energy. Okay, and then what you would have is a situation in which this energy exchanges a tree level, has a tree level exchange of gravitons between this energy source and this other energy source. Such a diagram could exist. Okay, now I'm going to argue that this is precisely what is happening. Okay, how do I argue this? Look, in this diagram here, what we have is now when we do this integral over the s's, what we get is a bunch of numbers. Now imagine that you had two sources, whatever they were, and you injected some momentum into this one and took that same momentum out of here. Then what kind of, from effective field theory, what kind of answer do you expect? By injecting some momentum into here, there's some coupling from this to whatever intermediate particle you have here. You've got a lot of intermediate particles, so these are the various closed strings of string theory. Okay, but what you would expect is 1 over k squared plus m squared over the whole spectrum of string theory, and then with some SI here, where SI are the couplings to the sources. Certainly at very long distances, this is what you would expect. Moreover, at very long distances, the things that would dominate this thing are the guys with the smallest masses. Okay? Now this is exactly the structure we see here. You see, what we are saying is one term, well, the big difference here is that we haven't put any vertex operators in the game. Had we been doing this calculation with open string vertex operators, 3 here, 4 here, then we would have seen exactly the structure. This k would have been the net momentum you put into the vertex operators here. This k would have been the net momentum you took out of the vertex operators here. By momentum conservation, they would have been the same. And we would have seen exactly this structure. Here it gets a bit disguised because there's no k. We're just living in the vacuum. So what we're seeing is this structure, but with k equals 0. Now this structure with k equals 0 for any non-zero mass is just fine. But if m is 0, you have a problem. Okay? So were you to do a vertex operator calculation, were you to do some sort of vertex operator calculation here, okay, you would see that in addition to these s's, there would be a coupling like e to the power minus s k square. And then when you do the integral over s, each of these numbers will get enhanced with the k square, and that would be the k square plus m square. Note that the numbers that appear here are precisely one for every oscillator state of string theory, and so occur precisely at the poles of the closed string particles in the theory. And you can check that the numbers work out right, exactly right. That the things that appear here are exactly where the masses work out. I mean, that's sort of built into the structure. Okay? So what we are seeing here is this. By turning on open strings in the theory, our theory has a new sector that has charges, that talks to, that sources all the closed string fields of the theory. Okay? Sourcing the massive closed string fields was no problem. We're going to come back to that in a minute. But sourcing the massless closed string fields was a disaster. And this disaster is what we're seeing in giving us infinity. What have we accomplished here? What we've accomplished, if you buy my words, is give an IR interpretation of this UV problem. Because we've got some effective field theory interpretation here. Okay? What has that bought us? Still, infinity is infinity. Giving some words to it doesn't change it. What it buys us, it helps us to think about the problem. So we know how to fix it. Okay? Let me say this a little more clearly. Instead of graviton, suppose we had a scalar field. So a model for a closed string sector, some closed string field is this plus m squared. The fact that it's graviton actually doesn't make a difference. It could be the dileton, for instance. It could really be the dileton. Okay, so we've got this object here. Now, suppose this is the model for adding into the open strings. It's like a 9-brain, a D-brain really. We add a j times phi, which is some object that has a source for phi. What was the vacuum of the theory? This j is translationally independent, space-time independent. Okay, what was the vacuum of the theory before we added the j times phi? Classically, it was just phi is equal to 0, obviously. Now, what is the vacuum of the theory after we've added the j times phi? Let's put a half here to make it a bit easier. So clearly, the vacuum is now j is equal to, phi is equal to minus j by m squared. Okay, so what we've seen is that we had this kind of restoring potential, which was localized around 0, and then by adding that linear term, we've shifted that restoring potential, so it's localized around somewhere else. If j is small, who cares? You expand around this new potential, everything's okay. This is a statement that adding a linear coupling to a massive field is no big deal. It can be dealt with in perturbation theory. You move the center, the origin of the massive field a little bit. But now suppose m was 0. This was not there. This is infinity if m is 0. Or if it was not there, just remove it. Now, what vacuum does this have? It has no translationally invariant vacuum. Now, there's a big difference between having a translationally invariant vacuum or not. So, massless theory coupled to a constant source just simply does not have the kind of vacuum structure that we expect. This is what happens when we try to study open string theory in the presence of closed string theory. The open strings are a source for the closed strings. The source for the massive closed strings was no problem, but the source for the massless closed strings was a big problem. And the problem was that we had a j phi coupling for a massless field. Every time you have a j phi coupling for a massless field, there's a name for that. We call it a tadpole. Tadpole. Okay? In this case, the field that would really get an really like to get it, I kept saying graviton. That's a bit inaccurate because the gravitons have indices. They're tensors. It's hard to give tensors expectation values. But there was a scalar, namely the dileton, for which everything I said was really accurate. Okay? So what we've done here is that the presence of open strings has created a dileton tadpole. A tadpole for the dileton field. So you'll hear this term a lot. There's a dileton tadpole. Okay? And this dileton problem, a tadpole, tells us we're dealing with a theory which may or may not make sense, but doesn't have the kind of vacuum we're interested in. Very much like a tachyon. Having a tachyon was not a sign of inconsistency, but it tells us that we're not expanding around the vacuum of the theory. Whatever it is isn't where we're looking. Would be something similar here, some striped phase or something like that, maybe, but we're not interested in that kind of theory. We want Lorentz invariant theory. Is this clear? Okay? So this dileton tadpole is the problem. It's really a little bit like the analog of adding a charge density all over space. Or even more clearly, if you want, take a compact manifold and add a charge density on that compact manifold. There's no solution to that problem because the lines of flux have nowhere to go. You can't. And adding charge all over non-compact space is sort of similar to adding charge on a compact manifold. Gauss law has no solution. Right? This is clear, right? Okay, great. So what we are discovering is this, that if we just try to add open strings to our theory, this theory does not make sense because the theory has a dilettante tadpole. This is another example of in string theory where you can't just do what you want. If you do the wrong thing, consistency will come and hit you. Okay. When we get to that part of the course, we will also see that some of these consistency conditions come from what is called anomaly cancellation, the constraints of anomaly cancellations. But you know, there are multiple ways of seeing the same thing, which is of course the nice thing about string theory. Okay, so what do we do? Well, maybe the theory of with open strings is not consistent. Maybe the only consistent string theory has only closed strings. That would be one logical possibility. But of course, people are inventive. Okay. Now, I don't know if you remember, but at some point we started studying the unoriented string. But anyway, whether or not you remember, we'll start it again. What we're going to do is this. We're going to try to introduce a new kind of string. Namely, we're kind of in type 2b theory, the left moving and the right moving sectors are identical because both of them have the same GSO projection. So in type 2b theory, one could imagine studying a theory in which one gauges the theory by symmetry that effectively interchanges left and right. Okay? It's gauging the theory by parity, because the parity operation interchanges left and right movers. Okay? We're going to start, next class we will study this theory. We will find that even in the closed string sector, for such a theory, there is a dilettante tadpole. We will find that if you have open strings in such a sector, in such a theory, just like here, there continues to be a dilettante tadpole. But we will find that
open oriented.
Open unoriented. It's not consistent to have the closed string sector unoriented and the open string sector oriented, because you know you can cut one to get the other. You know, in the end, you're doing Riemann certain kinds of Riemann surfaces with or without holes, right? So, however, we will find this. We will find that now we will carefully compute the coefficient behind the dilettante tadpole in every case, and we will find that if we add Chan-Paton factors to the open string and we make the theory unoriented, then if we add 32 Chan-Paton factors, the tadpoles will exactly cancel. We will also see, as I will have to show you, but we will also, you remember that in the unoriented open string, Chan-Paton factors give us UN gauge groups. In the oriented open strings, we will see that this gives us instead SON gauge groups in the unoriented open string. So we will find exactly one consistent open string theory with open strings, namely a theory with open strings and closed strings, type 1 theory, which has SO32 gauge invariants. You know, not SO16, not SO48, SO32, it's the only one that works. Okay, and that will, there we will encounter the fifth superstring theory. We've already encountered the heterotic theories. We've encountered the two heterotic theories, the E8 cross E8 and SO32. We've encountered the two type 2 theories. Now we will encounter the type 1 theory, and that will be the full set of Lorentz invariant 10-dimensional theories that we are.
Type 0.
Those are all tachyonic. Right. Okay. We will try to go through that analysis next class. Any questions? Okay, we'll stop the class here. Any questions or comments? Okay.
You just basically said that these are open strings and disconnected by some closed string, and closed string energies.
Yeah. Well, you know what I said is look what we're doing. At the world sheet level, we're looking at world sheets that look like this. And doing the modular transformation what did we do? Instead of computing trace like this, for the Hamiltonian like this, we're computing some sort of trace like this, we're cutting like this. That's clear? So now when you cut the world sheet like this, what Hilbert space are you seeing? You're seeing the closed string Hilbert space. That's clear, right? We've got one path integral. If you cut it like this, you're seeing open strings. But you cut it like this, you're seeing closed strings.
Yes. True.
Okay? Now, for every factor, for every state in that closed string theory, actually not everyone, those that have non-zero matrix elements, here. The matrix elements tie left and right together. So, but anyway, for all those that appear, you see a factor of e to the power minus s. So each of these is associated with one closed string oscillator. This is totally clear, right? Because we're just computing trace e to the power minus beta h this way. Is this clear? So the structure of this calculation is that we're getting one term here. For every term we're getting is associated with a particular closed string state. And this term came from the closed string state that had zero energy this way, which was the massless sector. So the problem is clearly associated with the massless closed strings. Is this clear? Now, the space-time interpretation of that is what? Having open strings gives a source that allows closed strings to propagate and be absorbed. Namely, a one-loop amplitude has two interpretations. Either it's a loop amplitude for open strings, or it's a tree-level exchange travel.
Closed string creating and annullating.
Exactly. And from this point of view, it's very clear why there was a problem. The problem was because there was a source for the massless closed strings. Just this dilettante tadpole. The problem that occurred in the UV of the open string path integral appears in the IR of the closed string thing. Because it's an IR problem, it has to have a field theory interpretation. Field theory is good, right? Because we're familiar with it. Okay? So it tells us that, you know, and also IR issues are not issues you can fix by regulation. IR issues are issues of physics. UV, you may want to try to fix it in some way, some technical way. But the IR issue is a serious issue. Okay? So by making this mathematical transformation to S, we understand the physics of the problem. The physics of the problem.
Which kind of interaction creates closed string?
Which kind of interaction creates closed strings? Okay, it's because there's a tension. Just there's effectively a square root g here, e to the power minus 5. Let me say it a little better. You know, the full amplitude for the open strings comes from a Dirac-Bonenfeld action. There is an e to the power minus 5 times determinant, square root of determinant of g mu nu plus alpha prime from 2 pi f mu nu. Okay, I mean we have a lot left to learn, but as we will go along, we will see that this is the kind of effective, we've not talked about this yet, right? No. This is kind of effective action for the open strings. F mu nu is the gauge field on the open string. Okay, so in particular, if you expand this to quadratic order, you'll get f square. You'll get the Maxwell term. Maxwell term you'll get a term which is square root g, f mu nu. Yes. All that's great. But in addition to all of that, if you just said f equals 0, you have this term.
Yes.
This is just a cosmological constant with an e to the power minus 5. So it's basically a cosmological constant. That's another way of saying it. Having the open strings forces the theory have a cosmological constant, but one that has an e to the power minus 5 in it. So phi will pick up an expectation value, but even more seriously, as you look at the problem more carefully, flat space is just not a solution even to the metric sector, because there's a cosmological constant. Space-time would have to curve up. Is this clear? We will see in quantitative detail at some point that this is how open strings couple to closed strings in the.
Supersymmetric Minkowski vacuum are solutions in string theory.
For type 1, for type
no,
2 theory?
In what theory is supersymmetric Minkowski space?
Type 2 is it's a solution for type 2 theory, for heterotic theory, and for type 1 theory.
Okay, all of.
Yes, but it would not be a solution for the putative string theory, where you introduce no unoriented strings and put some number of open strings. Let's say one open string. Now, in fact, as we will see, that theory has a more serious, maybe more or less it's hard to know, but another serious problem. That is, at the level of low energy, it's an anomalous theory. There's an anomaly, low energy anomaly in this theory, which exactly goes away if you're in the unoriented theory and there are 32 debriefs. So the same condition that leads to tactical cancellation also cancels the anomaly. So when something is wrong, you see it in many ways. And then when something is right, everything works. Is that clear? They will be D-branes, except they're 9 branes at the moment, meaning they're space-filling D-branes.
So they are heavy object when they change the...
Exactly. Change the geometry, that's what you're saying, right? Yeah. That's exactly what's happening. Notice, though, that the energy of a D-brane, okay, something I should have said. Look, we were looking at a loop diagram. So this was, in normalization in which sphere diagrams are 1 by g squared. This is a disk diagram which is 1 by g.
Yes.
This tells you that, maybe actually we were looking at the calculation we were looking at was a cylinder diagram, which is 1.
Yeah.
This is telling you that the effect we're looking at is small for the closed string sector, closed string sector. Why is it small? It's telling you that the source, while it exists, is order g. Because g times 1 by g squared gives you order 1. Okay? And this is the point here is that in a normalization in which Newton's constant is 1 by g squared, the energy of a D-brane is only 1 by g. Have I said that right? Did I get Newton's constant? Newton's constant is g square. Newton's square. The normalization in which Newton's constant is g square. Newton's constant is small. The energy of a D-brane is 1 by g, or energy of open string sector is 1 by g. This is the fact that it was a disk diagram or a cylinder diagram. Okay? This is why this divergent effect is not completely obvious from the closed string point of view. If you just compute the torus partition function, you compute the vacuum energy at leading order, at order 1 by g square, you see no problem. There's a problem, but at order 1. From the one loop open string contribution to this vacuum energy. I mean open string contribution. Okay? So it's a subleading effect, but it's a divergent effect. The subleading nature has to do with this fact, that it's got 1 by g coupling, whereas Newton's constant itself is g square. Is this clear?
So what are the sort of vacua allowed in type 1?
You mean apart from flat space?
Yeah.
Well, lots of compactification. So you could have Calabi-Yau type vacua. A lot of what you can do with type 2 you can do with type 1. but more because you have gauge fields.